Okay, great. I'm here in the University of Southampton as a lecturer, working as a lecturer in high energy physics. And my work is related to understanding the very tiny building blocks of nature. What are the tiniest of the blocks and how they interact, their dynamics. Today, I'm going to talk about a little bit about the quantum computing and how that can help us. I'm sure Eleanor gave you a very nice introduction to quantum mechanics already. Maybe some of the things I will just repeat just for the context to put everything in the context. But let me know if you have any question. So this is one of my very favorite quotes from Carl Sagan, who is a science communicator and an American astrophysicist. And it is like, if you wish to make an apple pie from scratch, you must first invent the universe. So the idea is that every child, probably from their very beginning childhood, has questioned like, what are those stars? Then you grow up in schools, high schools, the questions are, what are the smallest particles? When you are introduced to the concept of molecules, and then next you are introduced to the concept of atoms, which build the molecules. And then after that, what is inside the atom, nucleus, electrons. Then the question is where it stops, like how much we can break down all the matter and what are the smallest component. And then how these components work. You all know about gravity. You probably, most of you know about, radioactivity. You know about electronics. So all are like different kinds of forces that in action. So that holds matter together is different force than what holds the nucleus inside atom and the electrons together. So they are all different forces. So it's like our basic question, and that's why I have been interested in particle physics. Here is just some ideas of the length scale. So we start with a human body. If you go to the blood cells, you see from the scale of length scale of meter, we already reached micrometer. And as small as we go, there are so many zeros after the decimal places that keeps adding. So we go to the molecular level, which is say a blood molecule, which is a carbon molecule. And then we go to the nanometer scale. Then inside the atom, we go to the angstrom scale and so on. So we reach, for example, what is inside the nucleus, some protons, some neutrons together. And if we see one proton, we go to somewhere which is called femtometer scale. And you see how many zeros are there in the decimal place. So this is the kind of length scale we are talking about. And from here, where there are these atoms come in play, then we can't understand that world, the physics or that nature, that very tiny part of the nature in terms of our classical physics. And that's where the quantum physics comes. Now, as a particle physicist, what I do, I try to understand, like, for example, what is inside the proton? Like, what are the building blocks? If you see this red, green, and blue dots, like they are quarks. And quarks are some of the fundamental or the tiniest building blocks of the nature. And they are responsible for all the visible matter in this universe. However, how the quarks are there, like why they are not flying away. And they are connected by these strings, like things which are called gluons. And the force that is responsible for this is strong interaction. And that's where my research comes in play. And very typical thing about these quarks and strong interaction is that you would expect, for example, if you have two electrons with some electric charge, you know about Coulomb force, how Coulomb force behaves. It is 1 over distance squared. So it's inversely proportional with square of the distance between these two electrons. So if you take them apart from each other, the force really decreases as inverse square law. However, in case of these quarks, if you try to take them away, the force increases so much that you cannot take them away from each other. You can break the proton, but then again you will generate some quark antiquark pairs or quark quark three quark particles. So you would never see in nature one single quark, and that's fascinating because we don't understand that very well, and that's what I want to understand with my research, and this is due to the strong interaction. Another, for example, mind-boggling question. Let's say if you have one apple, and then if you have three apples, you would expect the mass of one apple or weight of one apple, what you have, say, some 5 grams or something like that. It's a too tiny apple. Then if you have, for example, 3 apples, you will expect 3 times that mass. Now, if you have one quark, let's say, although you won't find that, but prediction wise, we have the masses for them. If you have, say, 3 to 5, and this is our high energy unit of mass, which is MeV, mega electron volt, then if you have 3 quarks, which is a proton, you would see 1000 MeV its rest mass, which is so many more times, and definitely not 3 into the mass of this U quark. And that's also mind-boggling for us. We don't understand that from classical world, which is like, what we see around us. And this is due to all sort of quantum interactions at this level, at the particle physics subatomic level, and that generates this. So that's why this physics is so interesting, and we want to understand that. Now, what's the situation? How do we understand that? So there are 2 ways of understanding. One is that we have some theories which justify some experiments going on everywhere in the world, and we try to calculate them by hand, but it's so complicated at this level that only calculation by hand is not enough, and we have to go for large computation. And then there are direct experiments going everywhere in the world. You definitely know of CERN, you know of Higgs boson discovery. So in CERN, there are like particle colliders, huge ring, and within that ring, there are magnetic fields. The particles are charged particles, most of them. They are basically circulated in that magnetic field, gaining more and more momentum. They're accelerated, and that's why they are getting more and more energy. Then particle beams are collided together, which basically generates way more different kinds of particle jets. And then those new particles are basically detected as electrical signals. And from that, particle physicists analyze those data and know that which particles are there, what are the properties of the particle, and whatever our current understanding is. So what is our current understanding is this. Basically, this is more like a periodic table of particle physics. So what you have here in this table are quarks. Like there are 3 generations of quarks, so 6 quarks. There are leptons. So for example, electron is a lepton. There are neutrinos. Then there are muon, tau, which are basically heavier siblings of electrons. So they have similar type of electric charges, just their masses are heavier. Other properties are similar to electron. And then there is this particles which are inside that red block. It's the photon. You know about photon. For example, simple thing, photon is basically takes part in the electromagnetism. Then there are W bosons, Z bosons, and gluons. So WZ bosons take part in weak decays or weak interactions, for example, which are responsible for radioactivity. Then there is this gluon, which takes part in strong interaction, and this strong interaction is the reason for the proton, why the quarks are together holding inside the proton. And then there is this Higgs boson, which was basically the last missing piece in the standard model of particle physics, and which basically generates, which is the reason in terms of physics understanding, it generates the masses of these leptons, like electrons and so on. It is remarkable that after many decades of scientific endeavors and so much of investment, this table feels pretty complete. However, there are so many more questions beyond it that we don't understand. For example, dark matter, dark energy. For example, why there is no gravity included in terms of force. There are three forces. Among the four fundamental forces are included, but not gravity. So we understand there must be something beyond it. There are so many signals that there are something beyond it. It's just experiments and theoretical computation to find out what they are. So the strand at this point is that particle physics we are doing, theory, huge amount of computation, and there are experiments. Now, how the computations happen? So the computations, you all have laptops or you have seen computers. However, the amount of computation we need to do, it's not a small level. The data we generate are like hundreds of terabytes of data at a single moment. And then like one researcher is using that. This is shared between some other researchers, but everywhere in the world, like maybe, few 100,000 particle physicists generating data and trying to do computations. So there are some shared resources at the national level, UK national level, and every country has their own resources, which look like this. This is like a supercomputer. It's called Dirac resources, which I have given a photo from the facility that is in the University of Cambridge that I have been using for my research. And you see there are so many computers joined together. Basically, they are parallelized. So you can do computation, like many computations in parallel at the same time. So that's how classical computation is done. But now the question that I can ask is that our nature is quantum. So we have established that our nature is quantum at the subatomic level, where the laws of classical physics doesn't work. Quantum computation sometimes we cannot understand at the level of classical physics. It's kind of mind-boggling. But then the question is, why not computing our quantum nature or quantum world with quantum mechanics, using the principles of quantum mechanics and using quantum computers? Now, how we can do it? I mean, there has been huge work going on right now, but it's not accidental that people are thinking about quantum computing. It's a history that there are history more than like 100 years that people are working towards quantum computing, the nature. And the principles that, so I heard Eleanor at the very last minute saying something about quantum entanglement, and that's exactly two quantum mechanics principles that we need for our quantum computing. First thing is quantum superposition. Second one is quantum entanglement. And without them, without these principles of quantum mechanics, we cannot do quantum computation of our quantum nature. Now, I told about the roadmap. If you see this picture, which I got from a very nice website, it's basically history of quantum computation. You see where it started, 1900, with Planck's quantum hypothesis. So quantum mechanics has been born through many stages. There has been many paradox, Bell's inequality, which is one of the standpoint in the whole roadmap. There are this Feynman's quantum computer proposal and so on. So it's just generation-wise development of quantum algorithms, the ideas, and now coming to 2000, that's where we are seeing the fruit of all this 100 years of research, and that's exactly how science progresses. And then what we are seeing here is the development of first quantum computer, which is the ion trap quantum computer. And then as the years are passing, the progress is faster and faster in terms of actually building reliable quantum computers. So you see D-Wave, Rigetti, Microsoft, Google, IBM, and so on is just progressing at a lightning speed at the moment. And the whole idea is that what what are the aim of all this progress? I mean, the aim is infinite, obviously, like, uh, but at the moment, the aim is to make it to qubits, which I will explain what they are, to say a few thousand to 10,000 or beyond. So that's, we are at the, now it's called era 2 of quantum computation. And the devices which we are using are called NIST devices, which are near-term devices. So that's the immediate goal of quantum computation at the moment. Now, we discussed about quantum superposition and quantum entanglement. These are two principles on which quantum computation is based. What is quantum superposition? A very simple example, it's like tossing the coin. So if you toss a coin, it has two sides, head, tail. When it comes down to the floor, either it will be a head or a tail, and that would be 50% probability to get a head or tail. However, what happens that you throw it in the air, you don't see what's happening. Now, in the air, it is not going to be just a head or tail, but it will be in some angle of head and tail. And that's the state, what we call superposition. It's just a classical example, so it doesn't justify the quantum understanding of superposition, but just to give you some idea of what is superposition. So when we have the head or tail, that's the measurement. That's two states we can have, either head or tail. When we are tossing the coin, when it's in the air, it could be a mixed state, which is a superposition state. And that same concept, we then bring it to the bit and qubit, which basically the smallest unit of digital computation. So we are talking about digital computation, right? So in classical computation, you must have heard about bits. There are 8 bits which make a byte. Like it's a computer memory, how it stores information. Similarly, the bits, so in classical computation, the bits are 0 and 1. So you can think of 1 means there is signal, 0 means no signal. Or if you think about electrical current in the wire, so 1 means there is electrical current passing through the air wire. 0 means there is no electric current passing through the wire. However, if you mix them in qubit or quantum bit, or in quantum computation, they can mix and produce states in between 1 and 0 that we don't understand in classical physics, but in quantum physics that's possible. And that state is more like when the coins are in the air. So that's like a superposition of different states. That means in quantum, sorry, there is a typo. It should be quantum. So in quantum computing, parallelism is way more effective because in classical bit, let's say you have bit 0 and bit 1, even if there are two, so if you have n number of bits, either they can be in 0 state and 1 state, you have 2 to the power of n possible permutations. However, at a time, you can only access 1 state among these 2 to the power n possible permutations. However, if you think about the quantum bit, you have 0 and 1, but because of this superposition, still there are 2 to the power n states, but you can access all of them together in the experiment. Like you are doing a computation, you can access all of them. But there is, so it's like the parallelism, you can do that many processes in parallel, but there is a catch. And the catch is that even if you are doing all the experiments or all the computations in parallel, at the end, the measurement would either be 0 or 1. It's still in quantum bit when you are doing this parallelism. It's still after the measurement. So basically here, after you reach this state, when the coin is basically falls on the floor, either head or tail, this state, you still have 0 or 1, which means if you want to access all these states you have to access in a probabilistic way, and you have to do 2 to the power a number of experiments or more to have this many access this many states, which is practically impossible at the moment for any realistic physics problem or any realistic problem. But what we can do though, we can design some problems which is quantum in nature, which is not any general problem, but which is quantum in nature, that we can do. For example, a particle physics problem, which is the massive supernova, and the high density in that massive supernova, which are actually astrophysical system. And due to the massive density, we cannot do any direct classical computation. However, the quantum computation, it's by default, it uses a formalism, or it starts from it doesn't access or doesn't utilize the formalism of quantum classical simulation. And that's why we can directly use quantum computation for that kind of problem, like high density, high temperature. There are other situations like chemical potentials, which are more sort of like theoretical concepts, but there are very important physical situations that arise, which we can do with quantum computation. So we have to basically tailor the problem, which is quantum in nature, to use quantum computation. So that's the purpose of quantum computation at the moment. The second concept that quantum computation is based on is quantum entanglement. And the quantum entanglement, it's a very complex concept. So again, I'm just giving a very simple classical world idea. And obviously, it's very different in the quantum world. However, let's say you are now flipping 2 coins together, not just 1 coin. And what does it mean for them to be entangled? It means for them to be entangled that even if they are not talking to each other, if they are not entangled, then if you flip them, so you could have combinations like 1 head, 1 tail, both heads, this 1 head, this 1 tail, and both tails. So there could be 4 different combinations that you can expect from tossing 2 coins together. But if they are entangled, then the result will be different. So they both will be head or they both will be tail, and they talk to each other even if you don't understand how they talk to each other, how they pass that information. So that's entanglement. Now, if, for example, this means that you have an entanglement can go, it's the distance can be really, really large, like few million light years even, that's possible. And if you think about that here at a distance, at some space point, you have some information and that's changing. And then at a very large distance, you have another particle that's also knows what information changed here and it changes there. It feels completely puzzling. And that's what Einstein called this behavior a spooky action at a distance. And why he called that? Because he established that no information can travel faster than speed of light. That's the fastest. But if instantaneously, if you change something here and very large distance, it already knows that something is changed and that is changed. That means information, is it that information is transmitting faster than the light? Then there was a lot of research going on and it was proved that no, the information is not traveling faster than the light, because we are not talking about classical physics at all. It's the nature of quantum and its entanglement, which is absolutely quantum understanding, which we don't understand by classical physics. And because of that entanglement, again, if we have multi-qubit operations or computation, that can be much faster because of this property of quantum entanglement. Now, I have been talking about qubits. We all physicists love a bit of maths. Let's see what they are. So what they are, when we try to mathematically represent them, we use something called Dirac notation. And by Dirac notation, I have been calling superposition multiple times. So this psi here on the left side of this equation is like a superposition state. And then we have this 0, which you can think of as 0 qubit and 1 as 1 qubit. So again, in terms of trying to get some understanding from electronics, 0 means no signal, 1 means signal, or 0 means no current, 1 means current. And then alpha and beta are kind of coefficients in front of them. And this sort of mathematical expression where alpha is multiplied with 0, then added, and beta is multiplied with 1 and added together, this is called linear superposition. So that is how mathematically we realize superposition of two states in this wave function or psi. There is a concept called Schrodinger's cat. It's a very, how to say, very nice, very funny concept. And it means that, I mean, just simply that in quantum mechanics, if there is a cat in a box, it could either be in a living state or a dead state. And in terms of quantum mechanics, if you want to know the state of the cat, then it is either, it could be either of them. So you write them as a linear superposition of these two states. However, we always normalize what is this alpha beta. Their modulus squared basically give the probability for this cat to be in either the living state or the dead state. So that's why mod alpha squared, mod beta squared are very, very important. And it's called the normalization when mod alpha squared plus mod beta squared is equal to 1. So that's one way of mathematically representing the qubits. Another way, the same thing, you know about matrix, right? In mathematics, you have learned about matrix algebra. We can also write the states like this 0 with this bracket as a matrix, which is basically a column matrix 1, 0, and then 1, this state as 0, 1. And this psi state we can write as a column vector alpha beta with obviously with the same condition, modulus alpha square plus modulus beta square equal to 0. Why we write them like this? We write them like this because mathematically we want to understand what's going on. And next, when I discuss this, then you will know why. So now we understand the concept, like two principles going behind the quantum computation. We understand what are qubits and how they are mathematically represented. So how actually we do the computation? So again, expressing that mathematically, we start from a qubit. So we start from one state of, let's say, the coin. Let's go back to the coin, head or tail. And then this X, for example, is similar to in concept as to the the classical digital simulation, which is the which is the NOT gate. So basically, if you have 0, this X can make the 0 to 1, and it can make the 1 to 0, convert it to 0. So it basically flips the qubit like that. And if you implement that, after that, you have to measure. And after measurement, what you get is a probability of the state. So if 0 is there, X, this gate is implemented as a NOT or flipping gate, then you are going to get 1. So if you measure how much probability, so you are implementing that on this state, then if you want to measure how much, how much probability are there for 0, how much probability are there for 1. So it's a probabilistic measurement, which is different than the classical measurement, which is not a probabilistic measurement. So that's one difference of quantum measurement that we have using these gates. And here is a list of very different gates you can have. For example, X, Y, Z. There are C0 gates, which basically not just act on one single qubit, but it acts on 2 qubits at a time. Then there are Hadamard gates, Toffoli gates. So these are basic building blocks of a quantum circuit. Classical circuit, you might have done some experiments in the lab where you make electrical circuits. where different types of electrical experiments you do. So here also for the quantum computation, we need to make a circuit in the quantum computer. And for digital quantum computation, that circuit is made of these different types of gates. It can have many different combinations, and we can always optimize that combination to get the same result at the end. But it's these gates which are basically used. And this is the typical quantum circuit that you can see. For example, here, the operation is done with 4 qubits and 1 ancillary qubit. So which is an extra qubit that you need for the measurements to store data. And then there are so many different gates. So first, this plus and this blue gate, that is like a 2 qubit gate. Then on each of the qubits, X, Hadamard, and all these gates are used. At the very end, you see there are measurements. So these red blocks are kind of measurement blocks, and their measurements on 0, all the qubits separately to see the probability, like how the qubits have changed. So that's how quantum circuits are made. Now, this is one snapshot of the circuit. In a real computation, you have to do this kind of snapshot, say, 1,000,000 times. So that's why it's challenging with the current hardwares that we have at hand. Is for a realistic particle physics problem, we do not have enough hardware for the computation. Now, I have discussed this at the level of gates. I have discussed this at the level of mathematics. Now, in terms of hardware, although it's not my expertise, but obviously in terms of hardware, it has to be very different than classical computing hardware. Now, classical computing hardware, you know, if you have, I don't know if you have seen any computer chips, but if you have, for example, a very old laptop or computer at home, you might try to get to the motherboard and see what is there. So it's lots and lots of small chips, which are basically transistor. So transistor are electronic devices, which basically passes some currents and then block some currents. And that's why you get your computations done. In quantum devices, it's very complicated. The same type of electron flow cannot give you a superposition of all the states. So you have to have basic hardware principles different than just having transistors and chip. And that's why it is so challenging to build a quantum computer. It's not about just building it, it's about the reliability and robustness of the computation as well. And there are many candidates for this kind of quantum hardware devices. So for example, there are superconducting devices. There are trapped ion devices. So basically, if you have an atom, the ground state electron will be in the first, here in the first orbit. The excited state electron would be the next orbit. And then if you have pulsating lasers or something, then those electrons can just gain some energy, go to the excited state, release energy. And using this mechanism, basically there are trapped ion quantum computers. Then there are like other quantum dots, topological qubits. They also, some of the quantum computers use molecules. So there are many candidates for what could be like a quantum hardware. Question going forward would be, which ones are reliable? Would there be like all companies will use just one single technology to build the computers, or there will be multiple technologies still in the competition and different companies will use different technologies? It's all about the reliability and robustness of those computers. Now, quantum computers, obviously we understood there are many advantages. Obviously, there's this rapid calculations with unprecedented speeds. I already gave you some understanding of quantum superposition, entanglement, and you could expect for some problems like tailored problems, there would be exponential growth in speed. There could be efficient data storage capabilities, and there are many such, reliability of the computations, conducting complex simulations, which could not be conducted with classical computation. So there comes the quantum supremacy part. So definitely there are so much advantages of quantum computing that people are investing, and it's not just one group of people who are involved in this kind of development. We as high energy physicists or particle physicists, we are more interested in implementing our problems from classical computer and then implementing it on quantum computer for two reasons mainly. One reason is that there are some problems which cannot be computed directly on classical computers efficiently. And the reason number two would be more like the fast or robustness of the computation. But the overall progress is made by mathematician, computer scientist, hardware specialist, experimentalist, condensed matter experimentalist, material science engineers, and other physicists. And so it's a huge community effort rather than just a small community effort. Now, is it all beautiful things about quantum computing? No, obviously not. With all kinds of discovery, there are challenges. And at the moment, there are some disadvantages of quantum computers, or I would rather call it challenges. One of them is formulating algorithms. So for particle physics, like the type of problems I'm interested, if I want to build algorithms, formulating the algorithms even before putting it on the quantum computer is hugely challenging. And once I build the algorithms, that's not like one fit all type of algorithm. I have to basically tailor my algorithm or formalism for each of the problems. So that's a huge roadblock. Then the accessibility, like quantum hardwares, obviously it's very challenging to make those hardwares, like robust, reliable hardwares. But for accessibility to public or for research, it's also extremely limited. Then if you want to build, for example, the supercomputer centers, if you want to build a similar like quantum computer center, it's even more challenging than just classical computer like supercomputer center, because of the requirement of extremely low temperatures in some cases. Then navigating the challenges with internet security, that's also another roadblock. So there are like many roadblocks, but it's the same with all kind of scientific discoveries. It's not just specific to quantum computing that there are roadblocks. Now, if, for example, these roadblocks are eliminated step by step, where we can get benefit. So if we just see physics, we will benefit in all these areas of physics. We will benefit in condensed matter physics, cosmology, quantum information, atomic molecular optical physics, gravitational physics, high energy physics, nuclear physics. And obviously, this whole effort is going to revolutionize the advanced quantum technologies. So basically, technology will feed in physics, and the development of physics will feed in development of technology. Now, beyond physics, all the algorithms, all the formalisms, all the hardware, everything that we need in physics, that will also be shared. The advancement will be shared with many different areas of science. For example, quantum chemistry, quantum machine learning, quantum communication. So it's not a small community which will benefit from this huge effort. It's a large community. The whole science community will benefit. And there could be like climate science, other areas like cryptography. All these areas will benefit, like medical science will benefit hugely. Now, I will finish my talk with this roadmap, which is basically, the dream, basically the quantum resource development that's going on. Because as I mentioned repeatedly, that to address our particle physics problems or any problems at the large scale, we need many qubits, many of the order of 1,000 to a few of the 10,000s or 100,000 qubit quantum computer. Then we can do reliable and robust and meet the precision and everything in terms of our computation. And if you see this roadmap from 2019, already there were computers like Falcon, Hummingbird, which are like 27 qubits, 65 qubits computers. where we could start doing some computation and basically reproduce some results, which we can then could compare with the classical simulation results or our theoretical understanding, and we could test them already. And then coming to here, 2024, very recently, IBM at their New York Summit has introduced Condor, which is, and Heron. So Condor is more than 1,000 qubit machine, and then Heron 133 qubit. And then going forward, there are propositions of this Flamingo, Crossbill, and so on. And the idea is that by 2025, we might actually get a few thousand qubit machine. And then going forward after 2026, the plan is to scale it to more than 10,000, going forward to 100,000. But obviously, again, scientific discoveries, there are roadblocks. So this is the goal. It could be achieved by 2026, but it could take another year or two more. The question still remains that how to make them more reliable, more robust, and whether which technology will win or whether there will be parallel technologies. So I will just finish my talk here, and the floor is open for any question.